So, uh, good afternoon, everyone. If you are in Saudi Arabia, and thank you all for joining us today. Before I start, let me thank Air Products for giving us this opportunity to present to us about hydrogen mobility in general. We would also gratefully acknowledge Air Products for sponsoring some of our hydrogen mobility concentration students. We appreciate this so much, and we hope that this strategic collaboration between KFUPM and Air Products would continue in the future. Let me also thank the renewable energy and the hydrogen mobility concentration of the chemical engineering department for organizing this event today, along with the AICHE student chapter and KFUPM, as well as the young professional committee of the Saudi Arabian section of AICHE. So thank you all for co-organizing this event with us. So today we have actually a very distinguished guest from the industry. She's Michelle Schoonover. She's the manager of syngas technology team in Air Products in the US. She basically worked for 23 years as a process engineer dealing with hydrogen production and purification technologies. Michelle has a master's degree in chemical engineering from Villanova University, as well as a bachelor degree in chemical engineering from Western Polytechnic Institute. So basically, we have to be a leader in the industry in terms of hydrogen technology. And we are really interested learning from her and knowing her perspective, as well as Air Products' perspective on the future of hydrogen technology globally and in Saudi Arabia. So again, please join me in welcoming Ms. Michelle Schoonover, and the floor is hers. So please, go ahead.
Thank you so much, Professor Wall, and thank you all for joining today. It's a pleasure to speak to you about hydrogen as a central pillar for energy transformation. Hydrogen has become such an important topic lately, so I have many topics that I'd like to go through today. So please bear with me because it's a lot of information. So I will try to get through this and leave some time at the end for questions that you might have. So I'm going to begin with talking about hydrogen's role in decarbonization, and then get into some definitions of gray, blue, and green hydrogen. You may have heard these terms before, but I'd like to go through some of these definitions. I'll then talk about the hydrogen value chain, and then get into various hydrogen generation technologies, specifically to make gray, blue, and green hydrogen. And I'll also talk about some of the opportunities and challenges for hydrogen for mobility. So global warming is worsening. Reduction of CO2 emissions is urgently needed. You can see it all over the news lately, the impacts of climate change. If you look over the past century, you'll see that carbon dioxide emissions have been ever increasing and don't look to stop increasing anytime soon. And with this, the global temperature has also been increasing. As a result of this, we're seeing impacts to our world, our planet, such as melting of glaciers and more frequent, more extreme weather events, things like fires in Australia or the western part of the United States, major hurricanes, and all kinds of record-setting high temperature events and other sorts of things like that. So it's really important that we start to pay attention to the amount of carbon dioxide that we're emitting to our atmosphere. to really start to turn this around to preserve our planet for the future. So one way that we can obviously do this is to turn to use renewable energy, and in the form of wind, solar, and hydropower. That is one way that we can get away from the fossil fuels that we've been using over the past century and pulling up from the ground, releasing the energy, and then emitting that CO2 to the atmosphere. But renewable energy alone cannot solve this problem. If you look at the graph on the right, the pie chart there, you'll see, a breakdown of some of the sectors that emit greenhouse gases to the atmosphere. And what you'll see is that about a quarter of those sectors that emit CO2 to the atmosphere, it would be very difficult for us to eliminate those emissions using renewable energy alone. And so we need to find another way to do this. And some of those things that are hardest to eliminate are things like cement and iron and steel and shipping and long distance transportation. And these are all things that continue to grow as nations and regions develop and become more industrialized. So the graph that I have on the right, let me pause here for a moment to see if I can bring up a pointer. So the graph here that's on the right shows the global emissions by various regions in the world. And as you can see, in the early 1900s, it was primarily the United States and Europe with the Industrial Revolution that was starting to emit a lot of carbon dioxide. But as we progress through time and other nations and regions are developing, you can see places such as China where their emissions have expanded quite dramatically in the recent years, and other regions such as India and the Middle East, which are following the same trends. So we need to find a way to curb the CO2 emissions, that just naturally come about with nations and regions becoming more developed and more industrialized. So hydrogen can be that versatile carbon-free energy carrier that can help us to get there. So this chart here shows, again, a breakdown of the various segments that emit CO2. And there are some, such as agriculture and forestry, that we're not going to be able to solve with hydrogen. But about 65% of the sectors that are emitting greenhouse gases could be addressed with hydrogen in some way as we move forward, whether it be with building, and heating needs, or with other industries, transportation for sure, and even generating other electricity and heat and replacing coal in certain areas. So hydrogen has a big role to play in decarbonizing our world. But all hydrogen is not necessarily the same. So that brings us to the definitions of gray, blue, and green hydrogen. Gray hydrogen is what you would consider 95% of the hydrogen that's generated in the world today. This is hydrogen that is generated with fossil fuels. It is not low carbon. All of the carbon that goes into the process is emitted from the process. It is released to the atmosphere, and this is how hydrogen is primarily made today. But we're seeing a shift where governments are starting to enact tax credits and other such things to encourage corporations to decarbonize. And that brings us to blue hydrogen, where we can still use this renewable energy source that we have today, but now with blue hydrogen, we are capturing that carbon dioxide and not emitting it to the atmosphere. And rather, we're either sequestering it or finding a use for it in some other way. So that's blue hydrogen. And that blue hydrogen could be a stepping stone to get us from the gray hydrogen, where we're emitting lots of carbon dioxide, to blue hydrogen, where we're reducing our carbon emissions, and then ultimately to green hydrogen, which is completely renewable and very low carbon. In fact, with electrolysis, it can be 0 carbon dioxide emissions. So some examples here, I mentioned gray hydrogen is typically made with reforming. I have here natural gas reforming, although other hydrocarbon feedstocks can be used, and gasification. Blue hydrogen, again, you can use the same technologies you used for gray and put in a means of carbon dioxide capture, such as an amine system or an adsorption system. And you can also recover hydrogen from waste gas. And many refineries have waste gas streams that they would use as fuel that have considerable amounts of hydrogen, and we can recover that hydrogen and use it, and that becomes another example of a low carbon hydrogen source. For green hydrogen, electrolysis using renewable energy is 0 carbon, in that it is made strictly by adding electricity in the form of current to water to separate it. So the only products from that are your hydrogen and oxygen. But also some areas will recognize biogas and biomass reforming or gasification as a form of green renewable energy. And one thing I'd like to point out here that is with the biogas and biomass reforming or gasification, since those technologies do use a carbon-based feedstock, you can then employ the same technologies as we use with the blue hydrogen to recover the carbon dioxide and thus get to a negative carbon footprint in these cases. So now we're going to move on to talk a little bit about the hydrogen value chain. And I really like this particular slide because it kind of shows how hydrogen is like linking, natural gas and power together, and how powerful it really is. So here, I'll start at the top with the power grid. There are several different ways we can add power to the power grid. We can use renewable power, such as from a wind turbine or solar panels. We could use fuel cells, such as hydrogen fuel cells, and we can use combustion turbines to put power into the power grid. That power off of the grid we can then use for electrolysis by adding water and making hydrogen, and that hydrogen can go to end users. We can also make hydrogen in a more traditional fashion from natural gas or from coal or oil or other hydrocarbon feedstocks, and process that hydrogen, remove the carbon dioxide, and again put that into this hydrogen grid, if you will. And they also show here that we can even potentially take some of this carbon dioxide that's captured and go through a methanation process to make methane to inject in the grid. Or you could use biomass and clean that up and put it into the natural gas grid. But you see here how hydrogen ends up connecting our power grid, our natural gas grid, and ultimately we can use this to result in low carbon energy sources that can be used for downstream processes. So just another view of this hydrogen value chain. This represents, pretty much like the hydrogen value chain that we have at Air Products, where we take various kinds of fossil fuels or biomass or electricity. Natural gas is actually shown twice in this particular slide. I'll get to this one in a moment. But if we look at these hydrocarbon feedstocks we have at the top, for today, typically this is processed in either a steam methane reformer, an autothermal reformer, or a gasification process to generate hydrogen. As I've mentioned earlier, we can then recover the carbon dioxide from these processes and sequester or utilize it elsewhere. And then the raw hydrogen stream that these processes generate goes through purification, whether it be in the form of methanation or adsorption or something of that nature to get a pure hydrogen stream. And then that pure hydrogen stream is compressed or it can be liquefied. And in some cases, you can use geologic storage, such as a salt cavern, to store hydrogen, and pull that hydrogen back off of there if you need to. Another potential option is to store that hydrogen via pipeline, which Air Products does. We have some extensive hydrogen pipelines around the world that we use to supply our customers with hydrogen. And then hydrogen can also be supplied via, so this is the pipeline here, the tonnage, or by trailer, or if it liquefied, by a tanker truck. As we look to become more green with our hydrogen, we turn to using electricity for our energy source to make hydrogen, and that is done with electrolysis. And we can either use renewable energy to do this, or energy off of the grid. And when I say renewable energy, I'm talking direct renewable energy to do the electrolysis. In some cases, it may make more sense for people to recover the renewable energy and then add that to the grid. And then with the electrolysis, shown in both places here, we can either, same thing, liquefy that, or we can also take that hydrogen and compress it and send it to our customers via one of these methods. Natural gas is mentioned here because another thing that can be done is you could take biomass or biogas and clean it up and recover that methane from that feedstock and put it into a natural gas pipeline. We could go through the same reforming process then as we do up here, but again with biogas or biomass that's put into a pipeline, and reform that, purify that, and make hydrogen. So this is typically, the value chain for hydrogen today, and then hydrogen is utilized in many different areas today, including industrial applications, mobility, power generation, and gas energy. So many different uses for hydrogen downstream of this. So I'm now going to get into how do we make hydrogen? What are some of the means we use to generate hydrogen? Specifically looking at these different reforming and electrolysis methods. So I'll start with showing how different methods of generating hydrogen generate different syngas ratios. So we have electrolysis at the top here that generates essentially pure hydrogen. And then at the bottom here, we have our gasification technologies, which you can see produce a much greater amount of carbon monoxide with that hydrogen. So it's a much lower syngas ratio, if you will, of hydrogen to carbon monoxide in these regions. Steam methane reforming, you'll see, is very close to the top here in terms of the amount of hydrogen it produces relative to the amount of CO that it produces. And for this reason, steam methane reforming is generally the preferred method of making hydrogen today. Autothermal reforming is a close second in terms of the hydrogen to carbon monoxide ratio that we can generate with autothermal reforming. And I'll talk more about both steam methane reforming and autothermal reforming in a minute. And then, as I mentioned, gasification generates the lowest hydrogen to CO ratio. And then for each of these technologies, we can use pressure swing adsorption to generate a pure hydrogen stream to purify that syngas. We can also use membranes and again, either adjust the syngas ratio or purify the hydrogen. There are shift reactors that are used often across this spectrum to push the hydrogen to carbon monoxide ratio further up this curve, if you will. And then there are other ways using membranes and CO cold boxes and such to actually push further down this column to where you're trying to make more of a pure carbon monoxide stream. So now I'm going to get into a little bit more of the detail around how we generate hydrogen using some of these methods. So steam methane reforming, this is the process, as I've mentioned, that is most commonly used to make hydrogen at large scale today. It is a process that uses a hydrocarbon feedstock, and that hydrocarbon feedstock generally is preheated and sent to some sort of a pretreatment system to remove sulfur from the natural gas or other feedstock that's being used, because the catalyst in the downstream equipment is very sensitive to sulfur. The natural gas is then preheated in some sort of a heat recovery area. Typically, this stage of preheating will come from the convection section of the reformer. And then the natural gas is blended with steam that is generated via the process and is injected into the steam methane reformer, into these tubes that are in the reformer. These tubes are heated via burners that are spaced throughout the furnace. And because steam methane reforming is an endothermic process, and so heat is required, and the natural gas and steam mixture is reformed in these tubes, and then the hot syngas that's generated exits the reformer and is sent to a boiler where we generate that steam that goes back and is mixed with the natural gas. And in some cases, we also will export steam. The plant can be tuned accordingly, depending on how much steam our customers need. And the boiler will help to start the process of cooling down this very hot syngas stream. We then go into a water gas shift reactor, where we are further pushing the carbon monoxide and water that's within the syngas stream to hydrogen and carbon dioxide to boost up the amount of hydrogen that we're making in this process. From here, we pass through a heat recovery section where we use a series of heat exchangers to cool the syngas while we are doing such things as preheating the feed gas, preheating boiler feed water, and generating steam. After we cool the syngas sufficiently and knock out the water, we will then send the syngas to a pressure swing adsorption unit. A pressure swing adsorption unit is it's a cyclic process where we feed the syngas that contains approximately 75% hydrogen into one or more of these vessels, and we get pure hydrogen out the top. And that pure hydrogen then goes on to our customer. And then once these beds are saturated with the impurities that are within the syngas stream, including methane, carbon monoxide, carbon dioxide, nitrogen, water, those impurities are then purged from these vessels, and that waste gas stream that is generated is sent back to the furnace and is used as fuel for the burners, where it's mixed with a small amount of natural gas. So this is the overall cycle for a steam methane reforming system. This furnace, as I said, we have these burners, and the hot flue gases from these burners pass through the convection section, and then they pass out through a stack. So it is through this stack where we are releasing the carbon dioxide that is generated by this process. Because as you recall, I mentioned that all of the impurities that are in the syngas stream that are captured in our pressure swing adsorption vessels are then purged out and sent into the furnace to the burners. And so this is where the waste gases exit the process. So this is how we make gray hydrogen today. But now let's talk about how we turn that into blue hydrogen. So there are three options that we can use to decarbonize a steam methane reforming cycle. The first option is to recover carbon dioxide from upstream of the pressure swing adsorption unit. This carbon dioxide is at high pressure, and it's on the order of about 15 to 17% carbon dioxide in that stream, and the waste gas from the pressure swing adsorption unit is our second option, where we've essentially concentrated up that carbon dioxide in this particular stream. However, this stream is at very low pressure, probably about a third of a bar pressure. It's very low pressure. And then our third option for recovering carbon dioxide out of a steam methane reformer is in that post-combustion flue gas that I had mentioned in that convection section, where you could recover it there. But again, this stream is almost at atmospheric pressure, and so it is at very low pressure, and therefore much more difficult to remove the carbon dioxide. As such, the easiest way to remove carbon dioxide from steam methane reforming cycle is to recover it from the higher pressure process gas. In doing this, it's possible to recover about 50 to 60% of the carbon dioxide generated by the process in doing this. There are people looking at other ways to recover the CO2 from some of these other lower pressure streams cost effectively. But today, cost effectively, you can generally recover about 50 to 60% of the CO2 from a steam methane reformer. The one thing before I go on that I'll mention that's a big challenge with blue hydrogen is you need two things to make a blue hydrogen plant work. One thing is that you need somewhere to put the CO2, and the other thing you need is someone to pay for the CO2. Otherwise, this does not make sense. And so when we see projects emerging now looking at blue hydrogen, these projects are often being driven by local governments that are looking to start decarbonizing, and in some cases are actually coming up with areas under the sea where this carbon dioxide can be sequestered. So there are other opportunities. Air Products operates the carbon dioxide recovery system on SMR in Texas, and that system recovers I think it's 1 million tons per year of carbon dioxide that is used for enhanced oil recovery. So there are some other uses for that carbon dioxide, such as enhanced oil recovery, but in many cases finding that place to utilize that carbon dioxide can be challenging, and so people are turning to sequestering it in places underground at this point. The other thing I'll mention about blue hydrogen is that this decarbonization can be done for both new or existing plants. So I mentioned the unit that we have in Texas. That particular unit was a retrofit where it was not initially built with a carbon dioxide removal system, but was later retrofit into the system, which is nice because you can take a gray hydrogen plant today and turn it into a blue hydrogen plant, very easily. But then again, we can also build new blue hydrogen plants. So I want to talk about another potential way to do a blue hydrogen plant, and that is with autothermal reforming. So autothermal reforming is today often used for generating syngas for processes such as methanol synthesis. And it just happens to, if you remember that column that I showed, it generates a good syngas ratio for those types of processes. An autothermal reformer, again, uses a hydrocarbon feed, typically natural gas, again, preheats it, very similar to an SMR. Again, goes through sulfur removal, another reheating step. In this particular flow sheet, we're showing pre-reforming, which we can also have in an SMR. There is, I forgot to mention here, there's the steam addition, same as an SMR. The natural gas and steam mixture then passes into the autothermal reformer, where oxygen is used, and there's a catalyst in the bottom here. And so in this case, the heat generation and the reforming are all done within the same vessel, unlike an SMR where your furnace is separate from your process gas. And for this reason, that the heat generation and the reforming are all within the same unit, the all of the syngas is at pressure exiting the reformer. It's very similar in that there's also a boiler and another cooling train, just like an SMR. But with the synthesis gas at high pressure, we can do this CO2 removal in essentially the same location as an SMR upstream of our hydrogen purification. But here we can recover around 95% of the CO2 because we don't have that furnace with that flue gas coming out of the furnace with a very low pressure carbon dioxide. You'll notice here there is a fired heater. There are emissions from the fired heater, but they're very low relative to the amount of CO2 that's within the high pressure syngas stream that can be easily removed. So while today autothermal reformers are not typically used to make hydrogen, they offer a good option for making blue hydrogen just because you have so much of the CO2 contained within this high pressure syngas stream. And so chart, just to give you a little bit of perspective here, this is an SMR here, CO2 emissions with no carbon capture. And over here we have an ATR, again, CO2 emissions, no carbon capture. You can see they're about the same. And then when we add carbon capture onto an SMR, the recovery of the CO2 is, as I said, about 50%. And for the ATR, it's closer to 95%. And this is for the direct CO2 emissions here to look at the gray bars in this chart. Okay, and the final type of hydrogen generation I'm going to address here is water electrolysis. And this is a means of making green hydrogen with no CO2 emissions. So for electrolysis, we have electrodes and catalysts with low overpotential that allow for these high reaction rates. There's an electrolyte that's used in an alkaline electrolysis cell to provide high conductivity. And so a current is applied to this electrolyte solution, and we're able to generate hydrogen and oxygen. As you increase current, you increase the hydrogen flow rate, but there is a limit to the amount of current you can add because this results in efficiency losses and some thermal issues, and as well as cell degradation. One of the challenges, and I'll talk in a minute about some of the challenges with electrolysis, but some of the challenges are around scaling up of these systems. Another thing that is an operating concern, if you will, with electrolysis is the safety and reliability of these units. And that limits the operating pressures and temperatures of these units, because you want to avoid any kind of separator rupture or cross diffusion or electrolyte leakage. Here we have a couple of flow sheets for water electrolysis systems. These show systems that are made by Nel. And these are two different types. The first is the alkaline water electrolysis, which is what I showed on the previous slide. And the other here is a proton exchange membrane type of electrolysis. And the key things to note here are that these flow sheets are somewhat similar. The big difference here is with the alkaline water electrolysis, there's the electrolyte that needs to be added to the system, and then ultimately removed from the system, from the hydrogen that's generated. With the PEM, you do not have that electrolyte to be to be worrying about, if you will. So these are two types of water electrolysis that are being developed. The alkaline electrolysis has been around for quite some time, and is the more established technology, I'll say, today. With the PEM electrolysis, a lot of development being done in this area. And there's also, you may hear about solid oxide electrolysis, which is another type of electrolysis that is also being studied right now and developed. So some of the challenges of green hydrogen via electrolysis, the technology itself, it's as I mentioned earlier, there are scalability issues. Current electrolysis facilities using green power are of small scale. So if I presented this back last April, I would have been telling you that the largest was 10 megawatt, or sorry, excuse me, 6 megawatts. But now, more recently, there's been a unit that was started up that's 10 megawatts. That generates less than 3 tons per day of hydrogen, which is not a very large amount of hydrogen, but that is the largest system that is currently operating. You probably have all heard about the Air Products, Aqua Power, Neum announced project for a 4 gigawatt electrolysis system that will produce 650 tons per day of green hydrogen. This will be the largest system in the world by far, as you can see. And there are many others, or I shouldn't say many others, there are others who have also announced plans for gigawatt size green hydrogen projects. But the largest electrolyzer modules available today are about 20 megawatts. And so these units end up getting manifolded together to form these larger systems. So there are limitations on the size of the electrolysis stacks today. Another challenge from a technology standpoint with electrolysis is optimizing the efficiency and the capital costs. These are 2 other areas that people are working on today actively to make electrolyzers more mainstream, if you will, for hydrogen production. Also minimizing cell performance degradation over time. As I mentioned, as you try to push these cells harder to generate more hydrogen, you end up having more degradation over time, and that's something that, again, is being looked at to improve this for the future. And the last thing I'll mention here is dynamic performance due to intermittency of power supply. So when we're relying on renewable power, whether it be from wind or solar, the sun isn't always shining, the wind isn't always blowing. There can be periods of interruption, and during those periods, the electrolysis unit must be able to respond appropriately to that and ramp up or ramp down, or be able to be easily shut down and restarted to deal with these non-constant, if you will, power supplies. With using green hydrogen via electrolysis, another area of challenge comes with the renewable energy itself, in that these renewable energy plants, whether it be solar or wind, they take up a lot of space. So the numbers that I have here are not absolute numbers; they're rough approximations, because if you were to look, you'd find that the land usage estimated for solar or wind can vary greatly depending on who is quoting these numbers. There are some very large wind and solar farms in the world today that do generate gigawatts of electricity. But renewable power is, especially low-cost renewable power, is not available in all regions of the world. Some regions do not have an abundance of solar or wind available to them. It just so happens that Saudi Arabia is an excellent location for wind and solar power, and that's why Air Products had made the decision to move forward with the project with Aqua Power and NEOM in this location, because it's perfect for low-cost renewable power that enables us to generate hydrogen and then ship that hydrogen to other parts of the world where renewable power is not as readily available. And then the final thing I'll mention here is, an operability. When you have an intermittent power supply, there has to be some sort of a balance between the capacity of the wind and the solar generation, as well as the electrolyzer and the hydrogen storage. And you have to strike a balance there to get the most cost-effective solution that enables you to supply the downstream processes, which may require a continuous supply most effectively. And the final note here is, one thing that you do not get with hydrogen generated via reforming or gasification is an oxygen impurity in your hydrogen product. And that's one thing that needs to be remembered from a safety standpoint, is that the oxygen in some cases can be removed from that hydrogen product, or if it does not get concentrated up, it isn't a small quantity. But it's another challenge that we in some cases need to address, that we wouldn't have otherwise had to have worried about with reforming technology. So I'm going to shift over to hydrogen for mobility. I just have a couple of slides left here before I wrap this up. So hydrogen for mobility, what I wanted to highlight here is that today the world generates about 70 million tons per year of hydrogen. And over the next 30 years, it's expected that this amount of hydrogen generated in the world is going to expand 8-fold, which is just incredible. And when we look at the projections for 2050, it's expected that 29% of this hydrogen consumption is going to be for the mobility sector. So it's expected that we are going to be generating, by 2050, more than twice as much hydrogen as we consume today, just for the mobility sector alone, 30 years from now. So hydrogen for mobility, some opportunities and challenges. The transportation sector makes up about 17% of the global greenhouse gas emissions. So it does make it a very good area for us to focus on, right, to reduce those emissions. Battery electric vehicles are definitely the main competitor of hydrogen fuel cell electric vehicles, particularly for light duty transportation. So we're talking cars. The battery electric vehicles are very efficient and are very suitable for such a light mode of transportation. The fuel cell electric vehicles are expected to be more competitive than the battery electric vehicles when we get to looking at distances of more than 300 kilometers. And this is particularly when we're looking at like long transportation as well as heavy duty vehicles, you know, and you're thinking your trucks and buses and that sort of thing. Because the size and the weight of the batteries starts to become excessive for these heavy duty vehicles. And in addition to that, the battery charging time is long. And, you know, when you have a vehicle that you're using to transport goods or people or that sort of thing, you may not have the time available to wait for the battery to charge. And that's where hydrogen offers an advantage. Hydrogen vehicles, the fuel cell electric vehicles also offer an advantage for, you know, those people that don't have access to a power source for nightly charging. So, you know, something, you know, some people might not think too much about if they have a garage or something like that, or park in, you know, some sort of a parking garage. But there are some people that, you know, they park their car in the street every night. And so how are they supposed to plug it in? And in those cases, you know, hydrogen can offer an advantage over a battery vehicle. But one of the challenges that we have with fueling stations today is hydrogen generation at the station. Today, stations generally have hydrogen storage available. Hydrogen storage can be very expensive. And so, you know, there may be some cases where it's desirable to generate the hydrogen right at the source that you're going to, or right at the location where you're going to use it. But that becomes a challenge. And I highlight this because I just mentioned how it was a challenge to take the intermittent wind and solar power for electrolysis and use that with an electrolysis process that would like to be constant. And this is the exact opposite situation where you have a hydrogen generation system that wants to run continuously. And yet we have a fueling station where you may have vehicles fueling, you know, only 8 out of the 24 hours a day, or 12 of the 24 hours a day. So that becomes a challenge, similar to using renewable power with electrolysis. And then obviously the hydrogen infrastructure needs to be developed to continue to keep up with the rising demand. And this includes the production, storage, transportation, and dispensing of hydrogen. But as you can see here, the expectation is that the number of hydrogen stations that are, you know, that are around today, this is 2020 here, which is, you know, a couple of hundred in these various regions. We're expecting that to grow, you know, to be well over 1,000 in each of these regions, just by, you know, the early 2030s. So we're talking like 10 years away. So it's expected that there's going to be a significant ramp up in these fueling stations over the next 10 plus years. So in summary, you know, the use of fossil fuels to meet our energy needs is not sustainable. Our planet cannot tolerate us continuing to put more and more and more CO2 into the atmosphere. We need to transition to renewable energy to save our planet. And hydrogen is that versatile energy carrier that's carbon free and can be used to decarbonize many of the energy consuming sectors. And although most hydrogen is generated with fossil fuels today, blue hydrogen can be that stepping stone to get us to the green, completely carbon-free hydrogen. But there are many challenges to building that hydrogen economy, as I mentioned a couple of them here. But yeah, our world is counting on us to solve these challenges. And I think that with the program that the King Fahd University of Petroleum and Minerals has for students in the hydrogen for mobility area, all of you are going to, you know, provide a great amount of value to this growing area and helping us to get hydrogen more mainstream as the energy of the future. So that is all I had. I don't know if you want to open it up for questions.
Okay, thank you so much, Ms. Michelle Schoover, for this really excellent and very interesting and enlightening presentation. I'm pretty sure that many will be interested in asking questions. So, gentlemen, whoever is interested, please raise your hand, and we're gonna basically call your name. Okay, Hussein, go ahead.
Yeah, thank you very much. I have a question which is related to the cost of the hydrogen. It is obvious that hydrogen energy is a promising, a clear source of energy that would decrease the pollutants in the Earth's atmosphere. However, from the economical point of view, forcing the transition to hydrogen energy might or would increase the prices of energy bills or the cost of energy in general, as the cost, as a result of the cost of the process itself and the cost of the building infrastructure for the hydrogen energy. So the question is how to decrease the economical shocks that would happen in the market, energy market, and what are the future plans for solving this issue? Thank you very much.
Yeah, that's a great question, and certainly something on, I think, everyone's minds, as we look to, how do we, transition over to using hydrogen as the energy of the future. And, I think back to, this is very similar when you think about it. It was identified, several decades ago that having sulfur in gasoline and diesel fuels was bad for the environment, and it took legislation and regulations to be put in place. And when we started to desulfurize things, that also cost additional money. But nobody looks back now, right? To that. Everybody accepts that totally has helped our economy, and so our environment. And so I think that it will be important for some government actions to take place and everything to push us in this direction. But at the same time, technology advances are being made every day, where we're continuously looking at ways to make these systems more efficient and less capital intensive. So I think it's going to be a combined effort that will take place over years for us to get there. But I think that it's definitely a direction that we seem to be, the world seems to be very serious about moving in right now.
Okay, thank you. Any other questions? Go ahead. Please raise your hands. Yazid, please go ahead, sir.
Thanks, Michelle. My question is regarding the safety. Actually, this is my main concern. So the question is basically, to what degree can we say that it is safe to put hydrogen in our cars, in the vehicles? We know from chemistry that hydrogen is explosive substance. So there's concern about putting hydrogen in the vehicles. So can you elaborate on this, please?
So yeah, I am not intimately familiar with the safety precautions that are in place, but I can tell you that you know, the hydrogen vehicles you know, are safe. You know, when you think about it, gasoline also has its own safety implications, but you know, hydrogen is very safe, and we're continuously looking to make sure that the storage containers, if you will, that hydrogen is put into are very robust. But yeah, I personally am not intimately familiar with you know, some of the safety developments, if you will, that are going on in this area. But yeah, I remember sitting in a presentation years ago where it was said that there has been some studies done that you know, show that hydrogen in a vehicle with the storage containers, that sort of thing that we have, are just as safe as gasoline vehicles today. And there are many hydrogen vehicles on the road today, and thus far, you know, there have not been any safety issues that have been raised. So I think everybody's very cognizant of that, because when we're dealing with the public, right, you know, hydrogen has been in industry, and we strive to make sure we're very safe, but then when you take it to the public, it sort of makes it a whole nother level of safety that we need to achieve, and we're definitely committed to doing that.
Okay, I guess Mr. Muhammad Al-Alouni has a question. Muhammad?
You can ask your question.
Hello, I just would like to first thank KFUPM for organizing this very beautiful presentation. And I would like to thank Michelle for the nice talk. I do have a question regarding, as you mentioned, the green hydrogen. And recently there have been some papers talking about the non-oxidative addition of methane to produce ethane and hydrogen. I just would like to get her feedback if she has any experience with this reaction.
I do not.
My second question would be regarding the capturing of the hydrogen. I believe there have been several metal organic framework materials that have been reported to capture the hydrogen. However, I think the price is too high in order to capture the hydrogen. So in order to capture it, for example, inside like tanks, you would need such materials to do that. What are your plans for this type of capturing of the hydrogen?
Yeah, it's a great question, and certainly, as you mentioned, metal organic frameworks are an option for, you know, improving our storage of hydrogen. And as you mentioned, it is also true that they are expensive. However, there are more companies, you know, that are starting up now that are looking to make it their business to make metal organic frameworks, and you know, and in doing so, to reduce the costs of fabricating them. So I think that that's something that you know, we'll need to keep an eye on for the future, and continue to monitor, because certainly they could be a potential opportunity for improving hydrogen storage as we move into the future.
Okay, Abdelhadi, go ahead, sir.
I have one question about the gray hydrogen. Now, building CO2 collector next to a gray hydrogen generator, could this make it a blue hydrogen? And if yes, do you think this what would future happen for the hydrogen generating?
Sorry, I missed the last part. Can you repeat the last part of your question?
Abdelhadi?
Yes, okay. The last part is if this what will make it a blue hydrogen. Is this what the world will go for in the future?
So yes, we can take a gray hydrogen plant and put some sort of CO2 capture system next to it. You know, we can incorporate it into the flow sheet of the plant, and in doing so, we can then say that that is blue hydrogen. Did that answer your whole question?
But in the future, do you think that's what will happen, or they will build the new things for a green hydrogen?
I understand. Okay, I understand. Sorry. Thank you. So I think that today, you know, we have so many gray hydrogen plants that are in the world today. For right now anyway, it won't make economic sense to, you know, just abandon those plants to put in green hydrogen. So I think that you know, turning those into blue hydrogen plants is going to be that stepping stone to get to the green hydrogen. So I think that what we'll see is we'll see more blue hydrogen plants in the near future, and then we'll be slowly transitioning over to more green hydrogen plants, you know, in the years to come. But the blue hydrogen plants, especially for existing infrastructure, is a great way to reduce that carbon and make those plants more environmentally friendly. But yeah, I think at least for a period of time here, particularly on the existing plants, we're going to see the gray plants become blue plants, and even some new builds are going to be built as new blue hydrogen plants, and I think that's, you know, mostly driven by carbon tax credits in certain regions of the world today.
Okay, I have last two questions. I guess we passed 1 hour. So if you can please answer these last two questions, and then we can end it. So my first question is Air Products thinking about hydrogen carriers entering this business, like ammonia or methanol or liquid organic hydrogen carriers? And maybe that can be a way to get rid of the CO2 by producing urea, for example, or methanol. My second question is, you talked about membranes. Does Air Product already operate plants with catalytic membrane reactors or SMR and water gas shift, or no?
Okay, great. So for your first question about the liquid organic hydrogen carriers, yeah, so today it's difficult, if not impossible, to ship liquid hydrogen over a great distance. There are no commercial liquid hydrogen ocean going carriers that exist today. And so it is necessary, you know, as I said, with certain regions of the world, such as Saudi Arabia, being perfect for low-cost renewable power, it's important that we be able to ship that hydrogen great distances to be able to use it in other regions of the world. And so with the Air Products, Aqua Power, and NEOM joint venture, that project will actually turn that green hydrogen into green ammonia to enable us to ship it around the world, because it is easier and the infrastructure does exist to ship ammonia. But there are other forms of liquid hydrogen carriers, and certainly we are continuing to look at those other options to understand, you know, what are the most efficient means of, you know, for shipping hydrogen around the world, even if not purely in the form of hydrogen when we're shipping it. It's a very key part of this whole supply chain is, you know, how do we ship this green hydrogen? So yes, we are definitely looking in that area. With regards to your second question, which was
Catalytic membrane reactors.
Oh, correct. Catalytic membrane reactors. Thank you. Air Products today does not have any catalytic membrane reactors. We have looked at ceramic membranes in the past, and we continue to, monitor such things, but we do not actively operate any ceramic membrane reactors. Air Products does have a membranes business, but it's a polymeric membrane business, where we use those membranes to either adjust syngas ratios or purify hydrogen streams. So we can take a refinery off-gas stream that has a high concentration of hydrogen in it and run it through a series of membranes, and recover the hydrogen from that, which is a very nice process, because there are no moving parts to that process. So it's a very reliable process.
Perfect. So we would like to, as Chemical Engineering Department, we would like again to thank Ms. Michelle Schoonover, as well as all Air Products. First of all, for her excellent and very interesting presentation. Myself, I learned a lot from her. And also Air Products for their continuous support to KFUPM and for sponsoring our students. Again, we appreciate this so much. I would like also to thank the student chapter and the Young Professional Committee for organizing the seminar, and thank you all for attending. So I wish you all a good day, and thank you so much. And thank you, Ms. Schoonover. Thank you so much.
Thank you. Thanks so much for having me. Greatly appreciate it.